By the mid-19th century, medicine relied heavily on extracting active compounds from nature. Isolating morphine from the opium poppy gave doctors a standardized, reliable painkiller. If you walked into a pharmacy during this era, you would see rows of these extracts. Morphine was an established, highly effective tool for managing severe pain and coughing. But it had a physical limitation. Notice these two hydroxyl groups on the morphine molecule. Because they bond with water, they make it polar. This is a problem because the fat-rich blood-brain barrier strongly resists polar molecules. Doctors needed a way to push this exact pain-relieving compound into the brain much faster, without destroying any of its therapeutic effects. The traditional practice of boiling down plants had gone as far as it could. To get a faster onset, chemists realized they had to alter the physical architecture of the molecule itself. Inside industrial research laboratories, chemists began testing structural modifications to bypass these natural barriers. Building on earlier alkaloid experiments from 1874, researchers at Bayer in the late 1890s designed a temporary chemical mask for morphine. They took those two water-loving hydroxyl groups and chemically capped them with acetyl ester groups, creating diacetylmorphine. By masking the hydroxyl groups, hydrogen bond donors drop to zero, while its lipophilicity, its ability to dissolve in fats, spikes to 1.42. Bayer chemists kept the core active ingredient exactly the same. They simply built a kinetic delivery package around it, specifically designed to manipulate human biological transport. Because of its new lipophilic profile, the modified diacetylmorphine molecule glides rapidly through the watery environment of the bloodstream. When it encounters the blood-brain barrier, it doesn't bounce off. The acetyl mask allows it to slide cleanly through. But the mask is temporary. Biological enzymes shear the acetyl groups off, rapidly converting the package into 6-monoacetylmorphine and then directly back into standard morphine. The acetyl groups acted entirely as a biological smuggling mechanism, carrying the established drug past the brain's defenses, only to unmask and release the active opioid load all at once. Because the entire dose arrives in the central nervous system almost simultaneously, a smaller physical amount of the starting material produces a massive compressed wave of relief. To late 19th century clinicians, this specific dose leverage solved their primary problem. They possessed an agent that suppressed severe coughs and managed pain with exceptional speed and apparent efficiency. Confident in its superior performance, Bayer heavily marketed this acetylated derivative to the public under a new trademarked brand name, Heroin. This line graph compares drug exposure inside the brain over time. The gentle hill is raw morphine. The sharp, vertical spike is diacetylmorphine. The exact speed that made the drug fast-acting generated neurological shock. That steep curve acts as the engine driving severe dependence. The researchers who synthesized it achieved exactly what they set out to do. They optimized biological transport in an era before modern addiction neuroscience existed to warn them of the cost. Diacetylmorphine proved that we can manipulate a molecule's architecture to perfectly bypass human biology, but a highly efficient delivery strategy amplifies both a compound's therapeutic promise and its destructive potential.